What if the universe is written in a secret mathematical language? One we're only just beginning to understand. A language that could, maybe, finally explain the deepest mysteries of reality. Well, let's dive in. Because right now, some physicists are trying to write the very first dictionary for this hidden cosmic code.
So, why do we even need a new language? Well, to get that, we have to start with the biggest unsolved mystery in all of physics. You see, our entire understanding of the universe is, well, it's split right down the middle. We have two amazing theories, two sets of rules that work perfectly, but they absolutely refuse to work together.
On one side, you've got general relativity. It's beautiful. It's elegant. It describes this big, smooth, curved universe where gravity tells planets where to go and galaxies how to spin. And on the other side, you've got quantum mechanics, the brilliantly weird theory of the small, a world that's fuzzy, uncertain, and based on probabilities. They both work perfectly in their own realms, but the moment you try to get them to talk to each other, the whole thing just falls apart.
And I don't mean it falls apart by a little bit. I mean, look at this. Take the energy of empty space itself. Quantum theory predicts a value for it. Our telescopes measure a value for it. The difference between them? It's 10 to the power of 120. That is a 1 with 120 zeros after it. This is called the cosmological constant problem. And it's not just wrong, it's the most wrong prediction in the entire history of science. So that leaves us with the ultimate cliffhanger, right? What happens in the places where these two worlds have to collide? Places like the singularity inside a black hole or the very first moment of the Big Bang. You can't use two different languages to describe that. You need one single unified theory. And that brings us to a really bold and, I gotta say, pretty speculative new idea. A potential new language for the cosmos that some are calling quantum dark geometry. Now, before we get carried away, a really important disclaimer. The people behind this are super clear. This is not a finished theory. Think of it more like a what if. It's a sketch, an invitation to think about math in a new way. We are way out on the frontier of science here. Okay, so what is quantum dark geometry? At its heart, it's a new attempt to weave together general relativity, quantum mechanics, and that other huge mystery, dark energy. The core idea is to imagine space-time isn't just a smooth, curved sheet. Instead, imagine it's a fabric that has this extra dark, quantum texture woven right into its very fibers. So, how would you build something like this? Well, here's the basic recipe. You start with a smooth space-time we know and love from relativity. Then, you let gravity do its thing and curve it all up. But then comes the twist. You weave in a field for dark energy, and, this is the key, you create new quantum rules that can actually feel the presence of that dark energy. So how does this new language actually change the physics? Well, this is where it gets really fascinating. It's not just a new coat of paint, it's proposing a fundamental rewrite of the math we use to describe reality itself. At the very heart of this idea is a new mathematical tool called the quantum dark derivative. Now, don't worry about the symbols on screen. The important thing is the concept. Think of it this way. Normal calculus is great for tracking how things change on a smooth surface. This new type of calculus lets the geometry itself feel the little quantum bumps and textures created by dark energy. It's that new term on the right that lets space-time know the dark field is there. And the most incredible consequence of this new math, it actually leads to a modified version of Heisenberg's famous uncertainty principle. It suggests that the fundamental fuzziness of reality might not be constant. In places where dark energy is really strong, the very rules of what you can and can't know about a particle might change. It's a wild thought. Okay, an idea this big and abstract needs a really big problem to test it against. And this whole approach, the idea of adding quantum corrections to gravity, might just help us crack one of the most famous cold cases in all of cosmology, the black hole information paradox. The paradox is pretty simple. Stephen Hawking showed that black holes evaporate. So what happens to the information of all the stuff that fell in? Does it just get deleted from the universe? Well, these kinds of quantum-corrected models suggest something amazing. Check out this chart. It shows the black hole's mass shrinking over time. But look, it doesn't go to zero. The evaporation just stops, leaving behind a tiny, stable quantum remnant. So what about the information? This other chart, tracking entropy, gives us the answer. Just like the mass, the entropy, which is basically a measure of information, doesn't vanish. it stabilizes. This means the information isn't destroyed. It's safely tucked away inside this tiny, stable remnant, solving the paradox completely. A new geometry like QDG is exactly what helps us describe the complex quantum dance that's going on here. This 3D plot shows the quantum state near the event horizon. It's not a simple vacuum. It's this incredibly complex, roiling sea of interference. And it's these quantum effects that change the rules of evaporation and allow that little remnant to survive. Now, this is a beautiful theoretical picture, right? But it's just that, a theory. How could we ever find actual, real-world proof for it? Where would our cosmic detectives even start looking for clues that space-time itself is quantum? Well, the hunt is on, and it's happening on a bunch of different fronts. Scientists are sifting through gravitational wave data, looking for tiny distortions from their long journey across the cosmos. They're scanning the ancient light from the Big Bang for any weird patterns. They're even building super precise experiments on tabletops here on Earth, trying to see if space-time itself has a kind of quantum jitter.
And what have they found so far? Honestly, nothing. Zilch. Experiments have shown that gravity works exactly the way Einstein said it would, and we haven't found any evidence of space-time being noisy. Now, that doesn't kill the idea, but it does mean that if these effects exist, they have to be incredibly, incredibly subtle. The universe is holding its cards very close to its chest. Which leaves us right back where we started, with a tantalizing thought. We've seen a glimpse of what a new cosmic language might look like, and how it could potentially solve some of physics' deepest puzzles. The first searches have come up empty. But maybe we're just not using the right dictionary yet. Is it possible the universe really is written in a dark geometry, and we are only just now learning how to read the first few letters? Only time and a lot more science is going to tell us the answer to that.